Please take it away.
All right. Thank you for the nice introduction. And it's been very, very wonderful to be here for a couple of days. Thank you for the invitation and thank you for the warm welcome. Today, I'm super excited to bill it quite appropriately this talk for the first time. So that's going to be like first of the seminar series, first talk. And where the point I want to start at is kind of like this new edifice of data science we have these days, of like these kinds of incredibly complex models are like growing and taking over. This is from one of my favorite comic artists, François Chuiten, a Belgian comic artist that also does fine art. And this is called La Fièvre d'Orbicante. And in this story, this is a story of a little thing. So there's this mysterious artifact that kind of lands in the world that's like these little cubes. And then they somehow grow and take over the world. And they become these super complex things that dominate the thinking. And it's really kind of appropriate for the way like network science was in my life and all our lives. And I feel like we're at this point now where we have this big edifice of science we've been building for a long time. And sometimes, you know, it's good to sit down and look at this beautiful thing. But I also somehow like sometimes feels like the architect in this book whose plans are disrupted by this machine that keeps on growing and is like yelling in the cloud. These super complex models are like taking over the world. And it's really annoying. So I want to go back to the origin of that book, where that's how this big machine starts, like very simple models that we can understand and we can say things about the world in kind of an interpretable way. So this is kind of like my go back to origin talk, low dimensional models of networks. And what I'm going to talk about today are kind of these things where what I mean by low dimensional model of networks is we have like our data, maybe we gathered something from Twitter that's super complex, and we want to describe them mathematically as probability. These parameters might not be too many. We're not talking like large language model N. We're talking a couple dozen or one per node at most. And then what I'm interested in as a statistician nowadays is to kind of do the back process. So kind of presume models of the world and flip them on their heads and understand something from the model. And that's like maybe betrays my origins in physics, right? These low dimensional models, if we go back to the classical papers of network science, many which were done in these halls of greatness, they come from physics, right? This idea that we have a modeling approach where there's salient patterns we want to describe, like famously like scale freeness, for example, or clustering like this. We write simple mechanistic explanations for them, and then we get models of the world. But of course, that also builds on a different set of ideas that's kind of much older too. That's closer to the field I'm working on now, which is statistics and sociology, where they had these also very simple explanations of the world in terms of like literal low dimensional models. So nowadays we have vector spaces with thousands and thousands of dimensions, but in these old models, you could think of maybe like a space of nodes in a preference land. And when you're close in that space, then you get connected, and they were like literally one-dimensional. That's from a famous paper by Huff and collaborators. And this kind of ideas, of course, was also borrowed by physics and machine learning from famous papers that were kind of doing the same things in hyperbolic dimensions. And all these models, there have been like a couple kind of landmark reviews in recent years that are looking at these simple modeling approach and are kind of saying like, hey, they're like unreasonably powerful. So you can describe lots of things about networks with these simple ideas. So from like their clustering, their degree distributions, kind of everything with a few simple ideas. With maybe like there's kind of people questioning the breadth of these models. There's kind of limits, but they're still pretty good. And so today I want to talk about a few kind of vignettes of like work that's currently happening in my lab on these low dimensional representations. So what I mean, like small hyperbolic models where we have like a few parameters, not super high dimension. And my first vignette is going to be from work we've been doing with Simon and Antoine, who are two collaborators at the Université Laval. So this is led by Simon, who's a PhD student there, where we're working on these hyperbolic embedding from a Bayesian perspective. Okay, and just to like, I've been flashing images. I want to give you a bit of more like mathematical context for these things. These hyperbolic models, kind of a review, the explanation we give for networks with these is to take every node and give them a position in kind of a space. I'm not going to say more about what this space looks like. And then we compute a distance between these nodes. And the idea is that this distance should kind of encode some similarity between the nodes. Like if you care about the same thing, you should be connected, you should be close by. And that distance is going to be hyperbolic, but that doesn't really, it's not super important for the point I'm trying to make. And then we use a connection function and we say two nodes, if they have some distance, distance d here, the connection probability is going to decrease as you get further out. So that kind of captures similarity. We want nodes to be similar, to be close by. And then we say like our model for the world is just to take every edge and kind of flip a coin for every one of them and connect nodes at random with these probabilities. And that gives us a simple model. There's not that many parameters. We have one parameter per nodes. So again, like compared with the kind of large language models or machine learning models we have, that's 1/1,000,000th of the parameters we might have. And what made these models in the past super powerful is this idea of hyperbolic space. So the places where we put nodes are these spaces which are kind of like non-intuitive. They're not literal the physical space, they're hyperbolic. And so objects that are close by on the edges of these space are super close, but then as you go far, these distances become infinite. And things in the middle of these spaces are kind of close to everything in a kind of non-intuitive way. And just by choosing the space appropriately, it turns out we can represent data super well, kind of unexpectedly well. And the promise of all these models has been that like by formulating the simple models of the world, we can then like fit any data we might encounter. So originally that was the internet. This one is a famous embedding of a trade network. So every node in this network is a country, and then an edge encodes a commercial relationship. And so we can kind of find clusters of trades that make sense. So China is a very powerful exporter, so it's kind of the center of the space and exports to every other nodes in the world. Same thing for the USA. And then we have like these small kind of geographic subclusters. So this is Europe here, and we have like Saudi Arabia and more like Asia at the top. And these maps turn out to be quite powerful to kind of describe lots of things about network. And the way that's done is to take the data and take our low-dimensional model, so this probability distribution, and to say like what are the best positions of these nodes in this fake abstract space. So we solve an optimization problem. And that's been like really well understood how to do this for several years. So that's not where our contribution is. Our contribution is about rethinking how we do this fit. So we have this fit that's like very useful for routing, for lots of things, and we want to do it well. And the problem is that it turns out to be like very difficult from a computer science perspective to do this fit. It's a simple equation, but it conveys a lot of calculations of finding what is the possible best definition. And the reason why is that like, okay, it's still like low dimensional, but it's not like a simple line. You don't have like a single parameter you're changing. You're still changing quite a few. It's one position per node. And it turns out that this landscape of solution is rugged. So if there's like a solution here, maybe the best solution is close by, but there's a big valley, a big mountain you need to cross before you get to it. And so kind of searching is difficult. And there's also a lot of symmetries. So like if you think of these spaces, you can turn them around and it won't change the solution. You can kind of take clusters of nodes, move them around, it won't change the solution. So it's very kind of difficult to explore with our standard algorithms. And so what we did, we tried to do it in a Bayesian way. We used kind of modern toolkit, just try and like plug the solution and find with, for example, Hamiltonian Monte Carlo, stochastic gradient descent. And we found out that these out-of-the-box solution, kind of modern solution, didn't work. And that like the best next thing we had was this like years of work by doing that are a lot of little tricks that people notice over the years that kind of work okay. that are kind of brittle to like little changes. So if you change the solution, it doesn't give you the good one, or it finds kind of suboptimal tricks, and we can't really guarantee the performance. And so our goal for this project really to revisit these fitting procedures and find like high quality hyperbolic models. Okay, so for the reminder for people that are more familiar with these models, I'm going to focus on S1. That's like a specific kind of hyperbolic models where the parameters are basically just angles around a circle. Okay? And nodes that are similar should be kind of close on the circle. And there's a transformation that doesn't matter so much for our case about the degree. And so our goal is going to be, I take a network and I want to sample the positions of the nodes along this circle. And there's a probability model that tells me like what positions are good and what positions are bad. And to devise our solution, I want to give you like two intuitions about for why this might be a hard problem. So the first intuition is that like, suppose I know the position of every node along the circle, and I'm looking for the position of the last node. So I want to place it, this last node. And so here I have all the positions I can go from minus pi to all the way to pi, and this is going to be the quality of my solution. And what happens, this is well known from 2010, is that as I move the solution, I'm going to have like a lot of bumps in the space. And that comes from definitions of the models that basically say like you can't have two nodes on top of each other. So we move and then we meet the place where there's already a node, and it becomes like super difficult. And then we move again and we have a good solution. So we have all these bumps that are blocking the solution. And gradient descent really don't like these kinds of features, right? Because you have like infinite divergences. You can't really follow a nice gradient in machine learning through these. And further, they're kind of like worse with high degree kind of input nodes. So there's barriers everywhere in the space that come from like existing. So we can't get away with moving a single node at a time, for example. That's forbidden. Another intuition is that in this figure, I'm already also showing you the true angle of the nodes. Like I generate a network, I know where the nodes are, and then I try to fit it, I estimate angles, and I like do this figure with say like the best out-of-the-box algorithm, which is called Hamiltonian Monte Carlo. So that's like super fancy math, samples things automatically for us. And that doesn't work out of the box. That's kind of why we're doing this project. But one of the things we find is that there's kind of these patterns in what you fit where you will find sets of nodes that look like one another, right? You have the same angles more or less in the true solution, and they're embedded in a weird place where they're still together, but in the wrong place. So there's kind of this cluster structure to the problem. And so the solution that we devised with Simon looks something like this. So it's an idea borrowed from the literature of stochastic block models and so on. I think I saw your speaker series. You'll have like the world expert on this coming in a couple of weeks, but Thiago Peixoto. And in these moves, the idea is roughly our idea was to use the clusters to explore the space instead. And so in our Markov chains, what we did was to kind of find little clusters first, and then do transformations and move a lot of nodes at the same time. And things you can do is kind of find a cluster of nodes and flip it around, exchange it with a different cluster, or just kind of insert it somewhere else. And as you do these moves, you're moving super far into the solution space. And that kind of like takes into consideration the cluster structure. And it turns out to be not sufficient, right? If I can move a lot of nodes all at once, I can't do little adjustments. So we have a second step in the algorithm where we do kind of random walk to kind of just fit the small details, or we can do HMC and so on. And then there's a bunch of like bells and whistles. We need to like disambiguate rotations, graph isomorphism, but that's kind of more technical things in the background just to make sure that all the solutions are aligned. And this works beautifully. So there's a paper that we're almost done writing where we go from this. So that's what like Stan or like PyMC or any kind of machine learning models would give you to basically this, where everything's on the line. We're super happy with our results. And it gives us, unlike kind of standard models, these little error bars now, right? So we can say the true model, the true angle if a node is here, we estimated it to be true, but there's a bit of error. and we kind of quantify uncertainty now, which is actually a bonus. Okay, so I have a few kind of like more technical results to share about this, just for people who care more about the Bayesian stats details. So one of the cool things with this Markov chain we developed is that you can start basically from anywhere. So you don't need to know the true solution, and you converge to the right thing. So in blue, that's our solution. Whereas like Stan or Monte Carlo in purple, in orange, doesn't go to the right spot at all. And these numbers are like measures of how good your chain is at going to the right solution. And when it's close to 1, that's good. And so that's what we get. Another thing that Monte Carlo chains care about is fast decorrelation. So you want to kind of move super far, super fast. And that's also what we see. So, oops, my labels are wrong. So the red curve is us. The blue curve is just like a random walk. And this orange curve is HMC. So it moves fast, but it moves to the wrong spot. So we're kind of like worse off than them, but we go the right spot. So that's a trade-off I'm willing to take. Another thing you might care about is when you do these random walks, they're really costly. They take hours and hours to run, sometimes on big networks. So you want to be sure that it's worth your time to do this. And statistical machine learning people have this thing called variational inference, where instead of doing a random walk, you try to approximate your distribution with a normal distribution in a faster way. And so you don't want your samples to be normal, because otherwise that means that your Markov chain is kind of useless. And so when we look, for example, that's the position of a node, the position of another node. If we look between them, there's kind of weird correlation structure that's not a normal distribution. This kind of skewedness, right? So that's not described by a Gaussian. And so that's kind of like worth doing, even if it's costly, because the approximation won't be good. Okay. Okay. So I think like my partial takeaways for this first vignette was that, there is, from looking at these networks with this embedding, we found that like there's a lot of uncertainty actually in embeddings, right? There was like error bars on everything. And that like we actually need fancier Monte Carlo to do it, to do this. And so we were proposing a merge split way to sample from these models. And it works quite well. Obviously, this is the beginning of Simon's PhD, so there's like several opportunities, and we're always looking for collaborators to help out. So it turns out that it's like super slow to run right now, because you need to move things around, you need to do automorphisms at every steps, and so we're curious to hear if you have any idea. Like a couple hundreds. We can do like samples in like an hour. We're not doing GPUs yet. And another thing we're interested in is kind of like take our bag of tricks, these merge split, and throw them into existing like physics kind of optimization routines, and see if we can improve things with these moves. All right. So I started with like the most technical one. I'm curious if you have any questions before. Yes.
So the decision of moving from merge to split back and forth, is it like a dynamic based on some kind of performance feedback, or is it just...
So we're doing like a metropolis thing. So we have like a bag of moves, and then we like pick one at random so that the chain is equilibrated and invertible. So it's not adaptive. It could be maybe, but the simplest way to start is just a bag. Oh, nice. So you like decide to do a move when you need it. We should try that. All right.
And is it generalizable to high dimension?
That's one of our questions. I think so. You would probably need to find a way to split the two-dimensional space, right? Or three-dimension with maybe Voronoi diagrams or something like that. That could be fun. I know optimization people have been doing like Mercator to do it for optimization, so possibly a follow-up there. Okay. So second vignette, it was kind of chronologically before the hyperbolic, but I think it makes sense as a nice kind of like consequence of what to do with these low dimensional embeddings, right? This is a project with Alicia Patania, who's also at UVM, and Antoine is kind of the constant between these two projects. And in this one, we were looking at like a machine learning pipeline that's like as old as time itself. Like I feel like machine learning in the 60s was already doing something like this, or 70s. No, you have like your data originally, in this case a network, and then you embed it in a low dimensional space. So every node gets a position, say with hyperbolic embedding or something like that. And then you run some kind of standard clustering algorithm like k-means or something like this to find groups of nodes that are close by. And then you lift it back into your original data set, and that kind of lets you find groups. That's kind of one of the things you can do with embeddings. You can also do like prediction of similarities and so on. And this pipeline has been used everywhere, whether it's like not even, obviously not networks, but in networks themselves that's been used. In the context, for example, of hyperbolic embeddings, if we want to find clusters of nodes that are similar, we might run S1 embedding and then color the nodes as being similar. This is from a famous tutorial about ways to do it with spectral methods, like all these modularity detection were done this way too. And the problem, not really a problem, but the problem we wanted to address with the second project is that basically the state of the nation or the state of the union in this pipeline is that there's a lot of focus on the embedding step itself. Like all these like fancy new machine learning methods are trying to find the best locations. And once you have the locations, like things you do with the locations are not so important. And the reason for it, is that this second clustering step, so given nodes or points finding clusters, is kind of well tested. Like if you go on sklearn, the famous like Python machine learning library, this is like a figure I've seen so many times in my life just from Googling sklearn. You have like these 20 methods that are like super well coded. There's dozens of experts that have been working on them for years. And so they're fantastic. They kind of work, and they work more specifically when we have excellent clusters from the get-go. So when the positions we found are super good at like teasing apart groups. And so people like don't think so much about the clustering step anymore these days. And as a result, in network science specifically, when people started caring about using these hyperbolic spaces for finding communities, there's been kind of not a lot of focus on the clustering step. And so those are like my two favorite papers in this space. This one is the result of, I was talking about yesterday about how to do the science at a different pace. The one on the left is the result of one of these 72 hours of science workshops. So like these people came together and tried to like find communities in hyperbolic embedding, and they did this in 72 hours to archive. Impressive. And this one is out of a group in Indiana University that does very good work on network community detection and so on, the group of Filippo Radicchi. And these two papers, they kind of develop strong heuristics again, kind of very powerful bag of tricks. But it turns out, and this one was like kind of like a case of like, I know we can do better because I've seen algorithms elsewhere in computer science that can actually beat them. And so that's what we're going to do in this project. So our goal was to kind of revisit this idea of once you have the embedding, do a clustering in one dimension, but like a very good one. And so that's the problem we're trying to solve. I'm going to give you a bit of formulation, mathematical formulation to exactly what we mean. So we imagine that we have our nodes in a 1D space. In this one, I'm going to not even have it circular for now, just a simpler problem. So all the nodes are ranked. You can imagine this axis as being the angle. And our goal is to find communities, right? And communities in this context mean groups of nodes that are next to each other. So we'll call them layers, L, just for simplicity. And we suppose we have like some function that tells us like, hey, this is a good split. I'll call that Q, modularity maybe, or something like that. And it's a discrete optimization problem. So we want to look at all the layers, all the different ways of splitting them, and find the best one. So the objective could be like modularity, a cut, or a statistical model, maybe something like this, like a stochastic block model.
Number.
No, unknown. So Q here is unknown. It's kind of set implicitly by the algorithm. You can fix it if you want with like a penalty term, something like that. And okay, and it turns out that this problem, you can actually solve it exactly. So I can like tell you, here's a solution, and like guarantee you that there's no best solution. Okay, so you don't need heuristics. And the intuition for why that's true is that the problem can kind of like be decomposed in parts that don't touch each other so much. So if I ask you like, what's the best way to split all the nodes in the bottom quadrant in communities, you'll make choices there, and they might influence the choice at the top, but like not directly. They will kind of influence the solution next to it, and then that will propagate along the circle. And so that makes it a bit easier, right? It kind of, you can like divide and conquer, essentially. You can split somewhere and then split next to it and combine your solutions in a smart way. For computer science folks, that's called dynamic programming. It's an idea that was very popular in the 70s. And it's still popular when you have these problems where there's not that many interactions between the parts. I'll give you a bit of like main mathematical insight without going too much into the detail. But the quality of the optimal split, it turns out to be kind of, we can compute it by recursion. And so we can define this quantity Q, which is the best possible split of the G first nodes, the J first nodes. Okay, so the nodes, you like go from the top and you kind of stop maybe at the fifth node, and we like posit that this quantity exists. So what's the best possible split? What's the value of its split? And because the quality can be computed as a sum of qualities of different layers, turns out we can do this exactly by recursion. So what's the best way to split these nodes? Well, it's the best way to split the first nodes all the way to k-1 plus the last layer. And we can try every single one of them and suppose that Q exists and be able to compute them. And so by recursion, we can then like say this exists for Q of n, and therefore the solution exists.
It works for any.
Yeah, it works for any n, and then we like, oh, any f, yes. Any f as long as the function is additive this way. And basically then you recurse and you compute all the way to Q of n and you're done. I'm going to show you an execution of the algorithm to build the intuition further, but I just want to flag at that point that basically because this is dynamic programming, this is super fast. So in orange, that's kind of like the speed of the algorithm as we scale kind of bigger and bigger networks. In black, that's kind of like a lot of ways of doing this. And we're basically like as fast as the other methods, except like a greedy method that's a bit faster, but it turns out to like be super bad. So you don't want to do this. It's fast because it's bad. And so it's like, it's not costlier than anything else. It's exact and it's as fast as possible. Okay, so what I mean by recursion, let's walk through an example. Like suppose I have all my nodes ordered with some way, maybe like a hyperbolic embedding or something like that. I can index them. So I call the first node at the top 0 all the way to 61. And then by recursion, I start and I compute like the best way to split the first node in some number of communities, then the first two, and I kind of build this table of the best way of splitting the first K node all the way to 62. So I go down. And once I've done that, then I read it back from the bottom up. And I kind of remember the index of like where I found this best split. And then basically, once we've done this recursion, we can read it all the way back. I think this is way too small for people, so I'm not going to go through it in details. But we're basically able to reconstruct the solution by recursion. Okay. So like we have this magical instrument now that gives us the best communities in a super fast way. And we want to like look what it does in the world and kind of what we get from having this good instrument, this dynamic programming algorithm. So just to give you a bit of example of how that might change your outlook, we created these kind of fake networks, which have communities that are kind of correlated with the position. So there's like a yellow community at the top, then there's like a green one in the middle and a purple one at the bottom. And then we have a bit of noise, so we move nodes around. And we want to like recover those somehow. If you're a network scientist, you might pick from your bag of ways to do this. You say modularity maximization is going to be the way I'm going to find those. And we're going to maximize the modularity over all these 1D partitions. And so if you use our algorithm, you find 7 layers. There's a bit of noise, so you're going to find like more layers than you should, and that's okay. And you find a quality of like 0.49. That's a number in a vacuum. It doesn't mean much, but that's kind of the quality of our solution. If you do something like greedy, where you just kind of like at every step kind of try to put nodes together and do it without too much thought, you end up finding 500 layers and like a quality of basically 0. So that's what I mean by like greedy not being good. If you do kind of like what folks used to do before with heuristics, you actually find 5 layers. So you might be like, hey, this is a better solution, right? Like I had 3. The best way to do that find 7s, and this merge heuristic finds 5. So therefore 5 is better. But if you look at the quality, I don't know, we find 0.49. Quality of the merge is like 0.48. And so it tells us that basically like existing heuristics are maybe returning things that like look better, but that are like lower quality solutions. And so the failing of our algorithms is hiding kind of problems with our objective functions. And once we know how to optimize them, we can kind of find these errors. Too few solutions. Here's an example. Is a more difficult example where we basically completely remove the signal. The best solution find 26 layers, and merge heuristics find 12. So again, the objectives are, the clustering algorithms are hiding problems. Okay, so once we have that, we can kind of take the heuristic that we developed for a line and apply it for circular embeddings like S1 by basically taking a solution from the line and folding it back on the circle. And so this works with hyperbolic embeddings. We again have the best solution that's exact. So 0.74 as opposed to like 0.6, let's say, with the merge heuristics. And if you do this at scale, so this is my favorite kind of contribution, data contribution to network science, that's the ICON community net data repository. So that's like 600 networks on which you can test your ideas. It comes from the Closet labs in Boulder. And so we have these like 500 networks with various domains. Some of them are like biological, economical, transportation, and so on. And if you kind of like do S1 embedding and then community detection with heuristics versus with the method, we like see a small improvement. At worst, we're going to do as best as the heuristics, and we can only kind of do better. But the improvement is consistent. And the improvement kind of matters. So in this figure, what I'm showing is the quality of the partition we find with our algorithm Q, normalized by like the partition, the quality part of the partition you would find if you did like Gervin-Newman or like the fast unfolding algorithm. So a fast detection algorithm for communities. And those are like 500 networks. And so at 1, it's when like the embedding plus detection does as well as like fast unfolding. And in black, that's S1 plus exact detection. And you can see, and then in white, that's kind of the previous heuristics. And so before, people were like saying some things like, okay, we can use hyperbolic embeddings to find communities maybe, but heuristics is in the way, and we can't really do as well as if we detected optimally. So maybe we need to improve our clustering, was kind of like the claim of these older papers. And so now we improve clustering. We have now like the best possible solution. And so we can never go like above this as long as we're using hyperbolic embeddings. And we're showing that like even in the best possible case, we can do like as good as like optimizing directly communities. And so like our algorithm is basically revealing that like we have more work to do in this embedding step if we want to find cool clusters, because clustering cannot save us anymore. We're like as high as possible. And so that's a challenge to you all, like the next network scientist generation, like improve our hyperbolic embeddings, and maybe we'll be able to beat these 20-year-old algorithms finally.
In the objective function though, is modularity.
Modularity here, yeah. But that's kind of generally true with like any algorithms you might use. Okay, I'm gonna point out really quickly that like once I had that, it was like, oh, this is like an amazing tool. I want to like use it everywhere. I can do like something exact now. So we've been looking at a lot of systems. You know, there's like these linear embeddings might come from hyperbolic things, but you find them in different ways in the world. So you might have like rankings, like from chess matches and things like that, that are also ways of ordering nodes in 1D. You might have covariates, like age of people. You have a social network where people are stratified by age, and you want to find clusters of ages based on the network. You can use the algorithm for that. Any network centrality is like a number on a node, right? So you can use that to order your nodes and do detection that way. I found out, like, whilst researching that paper, a very old field in computer science called the graph layout problems. This is a survey in the CSIR by Diaz, beautiful survey. That's all about these old methods about placing nodes on a line, basically. So the algorithm can be used there. And yeah. And so my partial takeaway for this like second vignette, basically that like now, anytime you have like points on a line, a network on a line, we can break into layers at kind of no extra cost. So my pitch to you is that there's like no reason not to do this. We have our code online. It's called Divider. It's on Python code. There's a tutorial, so you can probably use it without too much of a headache. And I'm happy to take GitHub issues if you encounter any of those. And that like sweating these small details, it's just like a good way to do a simple thing right. Can actually have like big impacts on the results. So I think that's like a general lesson for like computer science algorithms. If there's like a good way to do a thing, just do the right thing, and it will change your finding in interesting ways. There's a number of opportunities. Again, we're interested in collaborators for those, kind of finding better embeddings now that we have the clustering done. And again, taking it with beyond one dimension is like not really clear how to do this for me. Yeah.
Charles has a question online.
Yes.
Is the gap between direct maximization clustering and embedding-based clustering due to the fact that the embedding itself doesn't carry enough information about the clusters themselves?
Yes, exactly. Actually, the gap. Yes, I think exactly. So like the communities are like spread across different networks, and therefore across different angles, and so you can't actually recover them very well because the embedding is bad. Yep. Guillaume first.
Thanks. The one thing that you taught me is that you might not want to maximize necessarily like your modularity function or something. So I'm curious, like, could you try? Have you thought about like using this dynamic programming tool as a way to sample or kind of like average over different potential clusters and stuff like that?
Yeah, I don't think it can in this case because it's like a search tool. So you might want to like use it as like a initialization, maybe something like that. And one of the things we didn't explore, like you can maximize sometimes. So if you have like a kind of good quality function, like say like a minimum description length, then maximizing is kind of doing the work of the average there. So that might be where I would take that. But yeah, like kind of hurts to be doing like maximal modularity because like that's a thing I've been railing against for a long time. But I think like the interesting idea to me here is like the routine, not the objective itself. Like you can swap in whatever you want. Was another question? Okay. Right. Okay, I have one more short vignette I want to talk about. I think we have time. Okay, so it's LLM decision making. So I've been like talking about these like simple, very simple model, but I've not escaped the craze. So we're gonna go more complex here. But I swear to God, there's a low dimensional model somewhere in there. And there's definitely a lot of interesting network science. And so this last project is with the kind of the newest crop of students in my lab, so Avi and Will. Brad is a postdoc at UVM. And here I have a couple industry collaborators, AI engineers at Borg ID and the Meta Institute. I don't know what happens when you go to industry for your professional headshots. Those are real people. And okay, so anyways, from working with these AI engineers, like everybody, I think we're kind of shocked by LLMs in December now 2022, more than a year ago. And we're experimenting with like two queries of the form of like, we're doing search queries in our databases and asking like, which of these is the most relevant? And then you give like two items, item 1 and item 2, and then you ask to the LLM like to rank them. And for people in person, you won't be able to see this very well, but for example, you might ask like, give me a strong American chess players. And maybe you have like two very random examples that don't really make sense. Maybe you're asking like Magnus Carlsen is one option. And then the other one is David Depto, who's a like chess boxing player and an American. And so there might be like an argument for the two of them being relevant in different ways. Like Magnus Carlsen is a strong chess player, but he's not American. And David Depto is literally strong and a chess player and an American, but he's like not a good chess player. And so like whichever you might like return is like a subjective judgment, basically, right? And the LLM will have like an opinion about which one is the best. This is a bit like of a cheeky example, but there's other cases where this is more serious or like more probable. So if you've been like taught to write English by like someone that has a lot of opinions, they might have given you like this trunk and white book that tells you like how to write well. And LMs have opinions about this, right? You can like say like, is this well written? Is this not well written? More like seriously, these AI agents have opinions about like what are good decisions when they start making automatic decisions with like self-driving cars and so on. And like maybe more relevant to us, like when we code, they might have opinions about like, should a code be written with spaces and tabs? There's a lot of like subjective judgments encoded in the way LLMs behave. Okay, so we found this, that there was kind of these interesting judgments happening with our LLMs, as everybody did. And this is like the way this is done in practice. In the machine learning papers are with like RLHF or VPO. They're kind of ways of encoding these preferences from humans and kind of teaching the machines to have the same as us, of like preferring spaces over tabs, because that's the obvious right solution. And so there's this amazing paper by Lambert and a couple of collaborators at OpenAI at the Allen Institute of AI that goes through kind of the story of how that's been done, kind of all the ways in the 1600s of like economics, how they talk about preferences. And like the very high level pitch is that these preferences between items, you can kind of like think of them as these scores. So like every item, let's say like a certain decision about which is the best American chess player should have a score in a latent space, one-dimensional, xi, and that's their position. And then whenever a decision must be made between like preferring I over j, you basically, that's a probabilistic judgment. So the answer is not like for certain, there might be noise, like depending on how the LM feels that day, they will kind of respond with a probability. That's the inverse logit of a ratio of scores. And that's super well known. That's the Bradley-Terry model that's been studied for decades. Recently, as was pointed out during the Erdos Rennie Prize Lecture for this year, turns out that we can think of this, as network models, where the nodes have again a position, and the preferences are encoded as edges. So if I is preferred over J in your data set, you place an edge from I to J, and then you get a directed networks of who prefers what over whom. Okay, and so our goal initially when we had these like preference data that from our users doing things with the system, we wanted to understand the decision making of these black box models by like querying them with Bradley-Terry. And the problem we ran into is that like it's not so obvious that LMs should have like coherent preference and like have a good graph of preferences. And there's kind of many reasons. You might have seen this online, the Shogot meme, where like the preferences are kind of learned from just looking at the internet, and then we like put humans on top to like make it a bit more palatable. Entropic, one of the big AI companies, has been trying to like tell LLM to behave according to a constitution, to prefer things in the same way that like the founding fathers of the US would. But that's like a lot of conflicting axioms, right? Like the Supreme Court is still to this day not sure about anything, and like they kind of revise out these constitutions, have different prescriptions for the world. And also this whole Shogot thing, right, of like all the internet contains very conflicting views about everything in the world. There's like a lot of text that says that Trump is a genius, and a lot of text that says that Biden is a genius, and they're like kind of like fighting and pulling in different ways that leads to paradoxes. Like LMs might not have like these beautiful trees of everything ordered in context. And so the thing we've been working on more recently in the lab is kind of this idea of mixture Bradley-Terry models, where we think that the LMs have like multiple clashing worldviews. And so whenever they like tell you, hey, I prefer this over that, they're basically pulling from their bags of worldviews, and then each worldview is a different ranking, basically. And so you can generalize the positions of items from like xi to xir, where r is like worldview, and then maybe you have like 30 worldviews or something. And depending upon kind of which worldview you pick, you will answer differently of I over J. So that's called a mixture model. So it's the same equation as before, but I now became like Ri, and then we have pi r, which is the like fraction of times the LLM will kind of call upon view R. And then your likelihood for everything, you just kind of take a product over all the data, and that gives you likelihood, and that's very standard at that point. It comes from social choice theory. Discrete choice theory. We know how to fit these models with expectation maximization kind of very fast. And so these models, these new models with a mixture of worldviews, turned out to like make interesting predictions about how LLM behave that kind of match what we've been seeing. So one thing that happens is that like if you have a single worldview and you kind of have like a bunch of rankings and you ask LLMs like, do you prefer I over J? And kind of you pick a lot of items, present them with the items and say like, which one is the best? You'll prefer like I over J a certain fraction of the time, and it will kind of depend upon your ranking. And as you add more worldviews in the mix, it will get kind of increasingly confused about what to say about anything. Because basically when you have three worldviews, like you compare two items, it will prefer them one way, and then you pick a different worldview, it will compare them the other way. And so it's kind of predicting this kind of increased confusion as the number of worldviews increase. That's a bit of an extreme. We're not saying that like LMs behave this way, but that's kind of like just to drive the point of what would be one of the testable implication of this mixture of worldview. Also, having these worldviews will kind of like make it much harder to decide what's the best. And so if you take a matrix here of like kind of the number of times that an item is preferred over another one, you can treat this as an inference problem and try to say like, what are these worldviews? And when there's a single one, we're able to do this, right? We have here like, these items in red are never preferred over the other ones. So if we rank an item 0, or like the first at the top, it's preferred always over the other ones. And the worst item is never preferred over the other ones. And once you mix worldviews, you're not able to do this anymore. So like the behavior you see is kind of not explainable anymore in terms of simple worldviews. So I just want to finish by saying, like with these models, what we've been doing now is we've been like putting LLMs to the test. We like gave them like maybe like 100 example of codes, and we're asking it like, which one do you think is the best code to do this task? And then we fit the model with like 1, 2, 3, 4 worldviews, and we're basically able to find what these worldviews are. And kind of recover from this mixture signal, what are they from just the behavior without being able to peek into the model parameters. And so like my partial takeaway for this final project is, as network scientists, we have now these like little machines that like behave in quirky and interesting ways. And there's a lot of tools in network science that can like help us kind of investigate them. So in this particular case, we're looking at preference models. And they work well for seeing these views, but like I encourage you to play if you've not been. I've seen kind of few papers recently doing like preferential attachment with LLMs and so on. It's quite fun, and it's like a way to try different things. And I think in this case it's also important because LLMs will get deployed, and we want have systems to understand really what they're thinking, and that might be one way to do this. Okay. So with this, that was my like old man yelled at the cloud talk, and so I like big models, but I was happy to talk to you about like simpler models with just a single dimension. There's still like cool things to be done, and so thank you very much for your time. I'll be happy to answer questions.
Questions for Professor Young?
So in this last part, so what would be the control of the experiment, the most controls on something? Very fixed data set?
Yeah.
What was the, so what would you do?
Yeah, and I think in the control, you like use your mixture model and you create data artificially and you try to recover them.
What the data?
The data would look like, A like I over J, which one do you prefer? And then you get a bunch of edges that way in a weighted directed network.
IJ
That's made up, right? And then very easily from there, you just go to actually asking an LLM to like make these decisions for you. It's in silico, so it's not very costly to do for small data sets. Yeah, I'm not sure does that answer your question? Okay. Yeah.
So yeah, very interesting, Mark. Thank you. So and last part.
Yep.
So I was wondering if you also want to develop explicitly within a particular worldview, or like so in kind of like a non-overlap, a non-democratic urban area,
Yeah.
old rural area, and then see like a bit work. Your goal is mainly fair in your worldview. So like that could be like a
yeah, I think so. That's the thing we've been wanting to do. We're still at the like early stages of the project. We like built all the inference pipeline when we tried it on a few data sets, but we want to like coax them and like ask them to role play as X or Y or something like that.
That is possible collaboration, because something that we recently used. So a lot of the variation that we did this in the case of a strategic decision and preference is multi. And one of the things that we noticed was quite a bit of the variation that seem to come from preference difference, come from actually the context of framing, because it's one with models.
Yeah.
So it's also crucial to control for the variation of context, which is a good component of this case, which is not the case for the general social discrete choice models. So it's an additional factor.
Yeah. So the way we set them up is like we basically start from a fresh context for every query so that the independence assumption holds. So there's no priming that happens. And so that we like start and we're just like, what do you prefer, X or Y? And then we have a couple of things to like steer the behavior where like we randomize the order or we like ask it to explain. And sometimes we have just a string of numbers to kind of push it into a high entropy mode to start. But yes, I agree. It's like super dependent on context. Thanks. Yes, and Sandra.
You try or think about this new way of things that for random instead for trivial.
Uh-huh.
Because I think in a sense, if I'm not an expert, but the thing that it does is generate, when you possibly generate different worldview, and then calibrate better trends.
Mm-hmm. Yeah, I didn't make the connection, I think, with RAG, but I think, yeah, it's like, do you see all the documents? It's like basically different worldviews, and then it's like basically picking.
In a way, I do this.
Yeah, I think there's an analogy there. Possibly the RAG pipelines that I know myself have like the choosing the worldview is like not the LLM itself. It's like a traditional kind of retrieval, and then